Bismillahirrahmanirrahim. Welcome students to the online lecture on digital logic design. And in today's lecture, we will be discussing the NAND and NOR based implementations. In the previous lecture, we discussed the prime applicants and not care conditions in the four variable K map. And in today's lecture, we will be discussing the NAND and NOR based implementation of logic circuits. First, we will be discussing with the NAND-based implementation. Generally, the NAND gate is known as the universal gate. It means that it can implement any digital system. Uh, Actually, because of the easier fabrication process, most of the Boolean functions are generally represented in terms of NAND and the NOR gates. So that's why we are discussing this topics because from the point of view of fabrication, this NAND gate is considered an easier to fabricate. What we will do is we will try to represent any given function in a form of NAND and the NOR gates. First, we will be discussing the NAND gate. If you remember, the NAND gate truth table, because it's the invert of the AND one, so we would have a value of 1 for all the combination except when the both of the inputs are equal to 1. And similarly for the NOR, it will only have a value of 1 when both x and y is equal to 0, and all other values it is 0. We will discuss here three basic gates implementation using the NAND gate. We will implement three types of basic gate. First is the inverter, then the AND gate, and then the OR gate. We will see that how we can represent these gate using a NAND gate. As you know, the NAND gate symbol is that you first draw the AND gate and then you put a circular buffer or inverter at the output. It becomes an AND gate. And if we want to represent any inverter using this gate, what we do is we just fuse both of the inputs together, because you know that inverter has only one input, x or y. So say if we have one input here, say x, and then what will happen is that in the truth table, if x is 1, then y would also be equal to 1. If x is 0, then y would also be 0. And from the truth table, in the last slide, we have seen that this would correspond to 0 and this would correspond to 1. So if you compare x with the output, you can see that it works as an inverter. By just fusing the two inputs together, our NAND gate will act as a inverter. And then we need to implement the AND gate, because in the AND gate we know that the NAND itself is represented by inversion of the AND gate. So if we put an extra inverter at the output, what we would get is we will get a xy complement here, and double complement here will again give us the x and y. So if we just add an inverter at the output of the NAND gate, it will give us the AND operation. So this whole function circuit is equivalent to applying an AND gate. Similarly, if we want to apply the OR gate procedure using the NAND gates, what we do is we invert the inputs. Both inputs are inverted here through this sum inverter, and we will get the output of the NAND gate as this. Because the inputs are inverted, we will get x complement y complement here, and because of the NAND gate, we will get a whole complement here. So if you solve it using the De Morgan's law, it will give us x or y. So in this way, this will perform the OR operation. So we have seen that using the NAND gate, we have represented the three basic logic gates that we have utilized so far. First one is the inverter, second is the AND operation, and this third one is the OR operation. So what we do in figure, if we want to change in the circuit diagram, if we want to change any or replace any gate or AND with an AND gate, what we do is instead of the AND gate, we will just or say instead of the OR, we will use this. We will just replace that OR gate with this one, and for the AND one we will replace it with this one, and for the inverter we will replace it with this one. This NAND gate can be represented in two different, you can say, symbols or graphical symbols. The first one is the called the AND invert. In this case, AND invert, we have the usual representation which we have seen so far, in which there is an inverter at the output of the AND gate. So this is a usual AND invert. There is another form which is also used. It is known as the invert OR form. In the invert OR form, this gate performs the same function as this NAND gate, but just its representation is a little bit different. Representation different in a way that all the inputs are complemented, and then they are fed to this gate or gate. And if you see that x complement y or y complement or z complement, it will just or all these terms, and which is equivalent to, by from the De Morgan's law, it is equivalent to x and y and z whole complement. So both of the final equations are the same. So these two are the same, represent the same NAND gate, but just a different type of representation. And now what we will be doing is we will, through example, will try to understand that how we can implement this is given any given circuit in the form of a NAND gate. Usually, it is preferred that the for the NAND gate implementation, the given circuit is in the form of sum of product form. Say like this, for example, in this example, we have four input variables A, B, and C, D. A, B are and similarly C, D are and the result is OR. So if we plot a normal two-level diagram of this circuit, it will be of this one. We have derived it quite often. So this represents a normal and or a representation of this example. Now what we will do is we will represent this in a form of NAND gate implementation using the NAND gates. We will use say three different type of representation to represent this circuit in the form of a NAND gate. In the first, what we use is we will use the AND invert thing, which we have discussed in the last time, of the graphical symbol of NAND gate, which is known as the AND invert. And we have seen that first what we will do is we will convert all these AND gates into the NAND ones. And we have seen that for converting any AND gate into the NAND gate, we require a NAND gate and we will put an extra inverter at the end. So what we have done is we will put an extra inverter here at the output. Similarly, for the second one, we have did the same thing. We have also put the inverter here. And now if you look at this OR gate implementation, so if we want to represent this OR gate in the form of this NAND gate, we have seen that we will have to invert the inputs. So we take a separate inverters at the input, and then we have the NAND gate. So this will give us the function f. And if you see that because there is a two complement process in the series, first this one and then this one. So actually we can cancel out both of them. Because two of them are series, they will result we know that the complement of a complement gives the original number back. So what we will have is we will have a direct connection from this gate to this one, which is represented in this figure. So for in this representation, we use the AND invert logic, and in this case, we have seen that there were two inverters in the series, so we have cancel out their effect. So this is the final circuit is implemented. So basically, this result of this one and this one is both are the same. We have just represented this function in a form of NAND gate in this figure. And now we will be representing the same function using the other form. In this form, basically, what we will be doing is we will be representing this function in using the invert or representation. And what is the invert or representation is in the invert or representation. First, we will represent this AND gate into the NAND gate, and the procedure is same, only the representation of this NAND gate is changed here. The rest is the same. We will put inverter at the output of our NAND gate, it will result in the AND operation. So we will have basically two level of implementation. This will be representing the N1, and this is representing the R1. And for the OR1, we know that the inputs must be inverted of the NAND gate, and for the NAND gate, we are using the invert or symbolic representation here. Again, you can see that both of the inverters are in series, so we can again cancel out their effect. And now you will see that this will result in this as a final diagram. And if you compare it with the diagram we have achieved in the last slide, is quite the same. The only difference is that instead of the AND invert representation, we are using the invert OR representation here. Rest representation is the same, because each of the gate here is representing the a separate NAND gate. Now we will see another representation of the same example. In this example, what we will be doing is we will be using a mixture of the AND invert representation and the invert OR representation. For the AND gate, what we do is we represent them in the form of NAND gate by using the AND invert symbol and placing an inverter after the output. Same here and same here. So both of these AND gates are representing using the AND invert symbol, and we have placing the inverter at the output. While for the OR gate, we are using the invert OR representation. This is represented by is a representation of the invert OR, and what we have done is we have placed the inverters at its input. Again, these are both are in series, so their effect will be cancelled, this one and this one. So the final or resultant equation will be like this one. So if you see that this generally, if you represent this in a mixed form, then it is quite similar to, you can say, the original diagram or the AND or gate diagram of the circuit. Because if you see that the AND gates are just replaced by the NAND gate, while this is replaced by the NAND gate, but it is representing in the invert OR. So if you look at the symbols, they are almost quite the same. For this one, what we have just inverted the inputs, and for the AND one, we have inverted the outputs. So all these three representation can be used. Most of the time, this mixed representation is sometimes preferred because it look quite similar to the one in the as the actual representation, because you can see that both of them are A and B are ending, and then the result is getting OR. So it is quite similar to this one representation. You can use any one of them, but generally this one is preferred. Now we will try to solve an example through a K-map. We have a three variable system x, y, z, whose minterms are represented as this 1, 1, 2, 3, 4, 5, 7. We will first try to minimize this using the K-map. So if from the K-map you can see that we can have we usually have three terms here. This is the largest square here, this, and then we have two adjacent square here and two adjacent square here. So this square will result in x complement y. This two adjacent square will represent in x y complement, and while this combination of four adjacent square will represent in z. So this is the final equation that is represented here. So if we want to represent this equation in the form of the NAND gate implementation, we can very easily implement it in a similar way that we have implemented the last example, because you have seen that this is the AND operation, this is again the AND operation, and the results of all three terms are getting OR. So what we do is, for the AND gate representation, we will be using the AND invert logic. So these are represented by the AND invert logic, and the final OR operation is represented by the invert OR logic. So similarly, you can also represent this in a form of the all of them representing as the and invert thing too. The process is the same, just only the graphical representation or the symbolic representation of the gate is the change. The procedure remains the same. So in this way, what we will do is we will represent any given expression in terms of the NAND gate. If you want to define it a form of a procedure, then we can write the few steps for it. The first step is that we should write the given Boolean function in form of sum of product form, and then for the each NAND gate for each product term, the input to each NAND gate are the literals of the term. And then we can see that a single NAND gate for the second term. So we can represent them in a form of the term wise. You can see that if there is a XY, we will have one level diagram for representation of this. If there is an other any AND operation between any other two input, then that would also occur in the same level, and then the result will be getting odd. But usually, all the Boolean functions may not be in a form of, you can say, a sum of product form. So if they are not in sum of product form, then what happens is we can represent that circuit in a form of a NAND gate, but that would not be in a, you can say, a two-level implementation. That would be changed to, say, three or four level implementation. Say we have a function like this. This function is not in a sum of product form. So we need to convert it into the NAND gate form. First, we represent it in a simple AND or gate logic form. This is the C and D operation here, and then you know that its result is getting OR with the B. We will get OR operation here, and then a whole result is then AND with A, and then we will compute this term here, BC complement here, and the whole result will be getting the OR with the first term. So this will give us the function. We can now easily convert it into the NAND gate implementation. For the NAND gates here, we will be using the AND invert logic to represent them. So we have represented both of them like this. And for this OR gate, we have using the invert OR operation here. Similarly, again, we have a NAND gate here. So we will be representing it in a more convenient AND invert form here. And the last gate is the OR gate, and we are representing it as the invert OR operation. I have cancelled out the terms which are double complementing here. So just to represent this simplification process. Say we have an other function. Again, it's not in sum of a product form. It's a function is represented as this. And the standard diagram representation of it is in this form. You can say a three-level diagram form. What we can do is we can convert it into the NAND form. Again, by following the similar rules, we will replace all the AND gate with the NAND ones. I will be replacing with all the OR gates with the NAND gate, but this time using the invert OR logic. So you have to clearly remember that the whole process is the same. You can use any of the two symbolic representation, either the AND invert thing or the invert OR thing. It will not affect the output of the system. Now we will be discussing the NOR based implementation. NOR gate is considered to be the dual of the NAND function, and it is also considered as the universal gate. That means you can convert all the expressions using the NOR gate. First, we will define that how we can replace the original basic gates of inverter or an AND using the NOR gate. For the inverter one, if we have this NOR gate, this is this most standard symbol that is used for the NOR gate. We put an inverter at the output of an OR gate. If we fuse both of the inputs together, then that would become an inverter, because say if x is equal to 1, then y would also be equal to 1 here. And from the table of the NOR, you can see that that would result in 0. So that would have actually inverted the input x. And similarly, if say x is equal to 0, then that would also make y equal to 0. In that case, from the table, you can see that output would be equal to the 1. So it act as an inverter if we fuse both of the inputs together. For implementing the OR gate functionality using the NOR one, what we do is we just place an extra inverter at the output, because we know this is the complement of X or Y here. So it will again be complemented. It will result in the original expression, which is the X or Y. Similarly, if we are representing the AND gate operation, for the AND gate operation, what we will do is we will invert both of the inputs. So if we are representing the AND operation using the NOR gate, we will use the NOR gate and we will invert both of the inputs. So that would result in this term, that original expression. We will get back the original expression, which is X and Y. It is also represented by two different graphical symbol. The first one, the OR invert, is the most common one, or which we have seen so far, and there is an other representation for this, which is known as the invert and procedure. Generally, for the two-level representation, we require that our expression is in the product of some forms. For the example sake, we have taken this expression and we will be converting it into the NOR gate representation. For inverting the first two expression A or B, we will be using the OR invert logic, which is here, and we will have an extra inverter at the output here. Similarly, the same for the C plus D term here. We will have, you can say, I will also draw inverter here, and we will also have an inverter here. And in the next step, what we will be doing is we will be in the second level, we will be ending all the three terms, the E, C or D, and the A or B. So for the AND expression, we have seen that we have to invert the input. So we need to add extra inverters here. So this will get cancelled out with this one, this will get cancelled out this one, and because of this inverter we have just written this as E complement instead of the E. So we will not have to write here now, because we assume that all the inputs are available in their original form and the complemented form. So in this way we represent a basic NOR gate representation of any product of some expression. See, this is the same example we used for the NAND gate representation. Now we are representing it using the NOR gate. We have just followed the same process here for representing the functions that are performing the AND operation. We are using the invert and expression or the symbolic representation, while for the OR operation we are using the OR invert expression. Both of them are performing the NOR gate functionality. We are just representing it so that from seeing the expression we can just judge that what kind of representation is that. So this is the same expression that we represented in the NAND one, and it is now the same we are representing this in the NOR one. Can you do read these pages from the book for a better understanding? Thank you.